So you know how I'm always checking to see if I'm recording with the right microphone? Well, I just did like a 10-minute long take before checking, and it turned out I wasn't recording. So that's why I check, is because very often, turns out, 1% of the time, turns out. Anyway, doesn't matter. So we're doing Chapter 2 of Artin, or we're starting Chapter 2 of Artin. We're going to probably read 2.1, which is Laws of Composition. Chapter 2 is on groups. And we're about to butt against what I call the most fundamental idea in mathematics, and that is the idea of quotienting. And if anything, I will say it's the central idea of mathematics, is that of quotienting. And so I'm going to try to explain it as best I can, and then I think 2.12 is something called quotient groups, which is, well, is sort of the idea of quotienting, is quotient groups. I think by the end of this chapter, you should have a full, good understanding of quotienting, which I think, again, is the central idea of mathematics. And then we'll get an even better idea. When do we start talking about group actions? Yeah, chapter 6. Yeah, where's group actions? I don't know. It doesn't matter, because I want to tell you about a little bit about quotienting. So, I have a saying that I say a lot to anyone who will listen. Don't stop recording. Go away, OBS. Which is that 99% of the difference between any two areas of math, it's more like 90%, is in their definition of equals. Now, there's a catch to that, which is what does it mean to have a definition of equals? Well, let me tell you. So one of the sections here is called Equivalence Relations and Partitions, and so that's kind of what I'm going to start with, is what is an equivalence relation. It's a very simple idea. So an equivalence relation is, well, if you want to think about it in function notation, it's a function tilde. So an equivalence relation on some set X, let's say, is a set, takes an X and an X and spits out true or false. If you want to think about it that way. But the rules are, every object is equivalent to itself. So this is called reflexive. Wow, I botched that. Reflexive. So if any relation which is a Boolean function on two inputs, any relation like this that has this property is called reflexive. It's commutative, which is that A is equivalent to B if and only if, or precisely when, B is equivalent to A, and a one-directional implication is sufficient here. So this is commutative. Symmetric, or I'm just going to write, no, I'm going to say commutative. Commutative maybe isn't the right word, or symmetric, something like that. And then if A is equivalent to B, and B is equivalent to C, then this implies that A is equivalent to C. So this is called transitive. And I'm going to give you an example over here. So the definition of equals in topology is something called homeomorphic. So a way to think about this is equals in topology means that no tool within the theory of topology is capable of distinguishing two different objects as long as they are homeomorphic. So a coffee mug here and a donut, or a torus, in topology are homeomorphic. Topology cannot tell the difference between these two situations. So, in other words, homeomorphism is an equivalence relation. Every object is homeomorphic to itself. If A is homeomorphic to B, then B is homeomorphic to A. If A is homeomorphic to B and B is homeomorphic to C, then A is homeomorphic to C. And then there was another option here, which was the spherical cow, which is, if you're familiar with physics, I can't remember, there's some joke that goes along the lines of, it's a common physics joke, which is, you know, something like some insane question about cow physics of, you know, how many cows can you get, or how long would it take a cow to do some X task, and the physicist does the problem and comes back to you with the solution and says, well, first assume that the cow is a perfect sphere. And so if you see something named spherical cow, I don't remember how the joke goes, it's something like that. I'm sure I just ruined the joke. So anyway, what I want to talk about, though, is this equivalence relation idea. This leads to the most fundamental idea in mathematics. So you have this, the two different fields will have two different ideas of what equals means. In group theory, our idea is called isomorphism. In topology, it's homeomorphism. In differential geometry, it's diffeomorphism. What this means, so the homeomorphism idea in topology means that you only sort of care about the, quote, fundamental shape, unquote, of the space. You don't care about, you know, silly details like its geometry. You only care about sort of how it connects to itself. Topology, I think, just means shape. Shapeology. Anyway, so once you sort of are presented with this equivalence relation idea, the natural question that you should ask, oftentimes, or this is the question that you ask, which is a very productive question to ask, which is, supposing I'm given an equivalence relation, what is a transformation that I can apply to an object that keeps it? Okay, and I want to introduce, this is called an equivalence relation, and I'm going to introduce some jargon. This is called an equivalence relation. And objects that are equal with respect to the equivalence relation are said to be in the same equivalence class. So in a sense, a theory is not capable of, a theory operates on equivalence classes, right? Topology, when you talk about a torus, you're talking about the equivalence class with respect to homeomorphism, or the homeomorphism class of a torus, which also includes which also includes the coffee mug. Is equivalence classes one of coset? That means the same thing as equivalence class. So here's a question, which is, what are some rules about functions that don't, so a transformation that I can apply to this, I can apply a transformation to the coffee mug to turn it into the torus and back and forth. Okay, so turns out a very powerful line of questioning and a very powerful line of argumentation is what happens, here, let me make this full screen, which is, what are transformations that I can apply to an object that keep it within the same equivalence class? So, let me switch. Let me just switch. Question. What transformations can I apply to an object given an equivalence? So we're in some context, we're in topology, we're in group theory, we're in something. What is a transformation that what transformations can I apply to an object that keep it, that doesn't change it, that transforms it into another object in the equivalence class, so doesn't change its equivalence class. Or let me just say, that keeps me in the equivalence class. Okay. What transformations can I apply to an object that keeps, that grammar sucks, but I'm Indian, so it's okay. What transformations can I apply to an object that keeps me in the same equivalence class? Well, let's take the class of transformations. So all the transformations I can apply to an object that keep me in the same equivalence class, and we're going to call these transformations, we're going to call these symmetries. This is our jargon. Okay, so what are our rules for symmetries? Well, we just copy the rules for equivalence relations. Namely, there has to be an identity transformation, which let's just call this E, which transforms every object A to itself. Okay, and this means maps to, this bar with the line. Okay. This notation is very sloppy. This means the identity transformation. There is an identity transformation. Okay. Next is that every transformation is reversible. So if I can go, so supposing that there's G, which maps A to B, then there must exist G inverse, which we denote like this, which maps B to A. So every transformation is invertible. What in God's name is this letter? Oh, it's the eternity AE. Every transformation is invertible. Okay. So this is equivalent to this rule. Okay, and then this third rule means that I have to be able to compose symmetries. Oh, I mean symmetry, not transformation, symmetry. So, same thing, but every symmetry. Every symmetry is invertible, and then 4, or 3, whatever number this is, I can compose symmetries. So if I have G, which maps A to B, and H, which maps B to C, then I also have H compose G, which maps A to C. So this is transitivity. And since these are functions, there's a fourth rule, which I'm going to write, which is going to kind of look trivial. But this is going to be kind of important because we're going to change our perspective in a little minute. A lot of insights in mathematics that you get are from looking at the exact same pattern of information and choosing to interpret it in a different way, which is associativity. Now this, if you think about the symmetries as operating on an object, then this is trivial because function composition is associative. But what this means is that if I have A circ B circ C, this is equal to A circ B circ C. Okay. Now together, all four of these laws define what is called a group, which is the subject of Chapter 4. So, 90% of the difference between any two subjects in math is their definition of equals. Well, once you have sort of a definition of equals, the natural question is, what are transformations that you can apply to a given object that doesn't change its equivalence class? Okay, well, by necessity, those transformations will form a group. We just proved it. So, then, there's another idea you can do, which is you take this idea and do it in the other direction, which is, suppose you have a group of transformations. Okay, and you have an object. Well, why don't you define a new object, which is the old object but this new group of symmetries is imposed, meaning you don't care if you change. If you change by this group of symmetries. And everybody who is watching this is already familiar with this idea because you all know how to read a clock. Okay, let me give you an example of a group. So a simple example of a group, we're talking about the group operation being addition here. And so you write this as z plus. Okay, this is a binary operator, so there's z plus that symmetrizes the integers. Symmetrizes. So for now we're thinking of a group as a set of functions that operates on another function or on another space. So maybe this is a little bit confusing, but it'll make sense. Okay, so there is a there is an identity. So if we take plus 0 with a, this is always equal to a. So there's an identity. Let me switch to a different color. There we go. There's an identity. It's invertible. So every transformation is invertible. So if I plus x, so if I have the transformation x adding x, then adding minus x does the inverse. So plus minus x times plus x to a. Well, this always just returns a. Okay? And then the third property is, the third property is commutativity, or the transitivity. Now, by that I mean, in this case, that this should give some insight, which is, what this means is that if I have a symmetry G and a symmetry H, then H of G is also a symmetry. That's what this means. Okay? And if I'm enumerating all of the symmetries, my group of symmetries has to have this property that when I compose them, I never leave the group. That's what this means. Okay, so plus y of plus x a. Okay, well, this is equal to plus yx to a. So, meaning that if we apply two symmetries, then there's another symmetry that I can rewrite this as applying a single symmetry. That's what this means. Okay, well, what if I so I have this group, Z, which is all of the integers, and I'm thinking of it as a set of operators on the integers. Well, what are the subgroups of Z? That's another important question you should always ask in math. I have some objects. What are my sub-objects? So my subgroups. And you have to be a little bit careful here, because in general you need normal subgroups. But since the integers happen to be a commutative group, meaning x plus y is always equal to y plus x, it happens to be every subgroup is a normal subgroup and a commutative group. But in general, you have to be a little bit more careful. And when we read further along in Artin, we'll get to why. But for a commutative group, this is fine. So subgroups of the integers. Okay, I'll just tell you, it's these things which are denoted as nz. Now, what this means is 0 plus or minus n plus or minus 2n plus or minus 3n, etc. Okay. These are every subgroup of the integers is one of these. So an example would be 2z, which is all of the multiples of 2. So this is 0 plus or minus 2 plus or minus 4, ... And in particular, we're going to focus on 12z, which is all of the multiples of 12. plus or minus 12, plus or minus 24, plus or minus 36, etc. Okay. So what happens if instead of symmetrizing the integers with the integers, we take our integers and we say, I don't care, what I'm going to do is define this new object, and I'm going to call this z divided by 12z, and this is called the quotient of z by 12z. This is called a quotient. And what this means is I am defining objects in this new space to be equal if they differ by a multiple of 12. Well, what does this give you? Clock arithmetic. And generally, z mod nz gives you modular arithmetic mod n. I'm assuming you've seen modular arithmetic. Modular arithmetic mod n. So there's actually more to the modular arithmetic because multiplication works in modular arithmetic, and sometimes division even works. And so for that, we're going to need something a little bit more sophisticated than this group abstraction. But this is the idea. This is why this notation is what it is, because it's quotienting. You're taking the group z and dividing out 12z. You're saying I don't care if things differ by 12z. So just right. I've talked about mod 2 arithmetic quite a bit on my WSC playlist, so you can go watch that if you really have never seen modular arithmetic. Mod 2 arithmetic is sort of the simplest trivial case, and it's a very beautiful application of it. What else was I going to talk about? Oh, I wanted to give another example. Okay, so we're our pattern here. So generally, it turns out that a very worthwhile thing to study in math, and people spend their whole career studying it, is to study what kinds of groups are there, to study the theory of groups. So instead of thinking of the group as a set of functions that have these properties operating on some other space, that is a very useful thing to think about, and that's called, the term for that is group action. Term for that is group action. So instead of thinking about groups as being things that symmetrize another space, the approach now in mathematics that the CIA has popularized is to study groups just for their own sake. You can learn a lot by just studying groups. Group theory, I think, starts with Galois studying some sort of group structure on root systems of polynomials, and I learned Galois theory once, and I have since forgotten it, but it's the last chapter in Artin, and so we are going to learn the CIA's Galois theory project, and then I will probably dig into Wildberger claims to have made a replacement for Galois theory that's better, and after WF algebra, and Wild Trig, I sort of just believe whatever he says, so I got to look into that. I'm paying $5 a month for his YouTube, for his premium YouTube, and I haven't watched a video in a while. I need to get back onto that. He started quoting Vladimir Arnold, who is one of my favorite math authors, but is kind of not the easiest to read. And anyway, so what was I saying? Oh, I wanted to give another example, which is let's switch to white because I'm tired of yellow. Let's take the two-dimensional Euclidean plane. So this is Q2. Okay? Two-dimensional Euclidean plane. And we're going to mod out by Z2. So what this means is I'm going to mark roughly the integer points. I'm just eyeballing this. Okay. I'm just going to quickly draw. Those lines are too thick. Don't you love my equally spaced intervals? Anyway, so in a sense, we can sort of almost partition the grid in this way. But what I mean is that I'm going to pick a pink point, and I'm going to zoom in quite a bit on this photo, or on this image. I'm going to pick this point right here. And what I mean is I am now declaring that I cannot tell the difference between any of these points. Sorry, it would work better if I actually had drawn these equally spaced, but I think you get the idea. That I'm now sort of imposing this movable lattice structure. I cannot tell the difference between any of these points because they differ by an integer coordinate. I'm not going to draw all the rest of them, but I'm going to give another example. You get the idea. This point. So in a sense, the term for this, by the way, is orbit. So I'm considering the orbits of Q2. I might have that terminology wrong, and if so, too bad. Under the action of Z2. Okay. Looking at the orbits of Q2 under the action of Z2. And you get the idea. I'm sort of have this movable lattice structure. Now, in other words, maybe another way to think about this would be, well, I'm just going to take a square. And I'm also going to consider for a moment the way directions work. Because another type of symmetry I might impose is something that takes would take this where's my green point? Would take this green point and move it up here, and then move down here, and then move up here. That's actually another completely valid group of transformations, but that's not what I'm talking about. So when you're talking about this, you draw which edge you draw sort of the this is called the fundamental domain. And topology people are going to email me, and I don't care about your tears because topology is a CIA psyop, so go away. Fundamental domain, okay. This edge is identified with this edge, and this edge is identified with this edge. Okay, so I encourage you at home to take a piece of paper. Let me find a piece of paper. And just fold it so that the two opposite edges meet in one way, and then pretend that you fold it so that the opposite edges meet in the other way. And in that way, you get a torus. So this is the typical way that a mathematician thinks about the torus, is as Q2 or they would think in terms of the CIA's real numbers, but as Q2 mod Z2, or as R2 mod Z2. That is the tip that if you ask a mathematician what a torus is, they will tell you it's R2 mod Z2. And they will tell you a cylinder is R2 mod Z, and a Mobius band is R2 modulo a group of glide reflections, something like that. Yeah, so Mobius band, in mathematics, the Mobius band goes infinitely far in both directions here, and then you do the glide reflection thing, so you do the reflection and also flip a coordinate, or something like that. I may have gotten that wrong. Anyway, then it looks like this. Or no, the glide reflection is, I think it's a reflection plus a translation, something like that. Anyway, that's how you do a Mobius band. And then if you glue up the edges of the Mobius band, then you get a Klein bottle. Anyway, so that's a little bit of topology for you. But we're not here to talk about topology. I just want to illustrate that this idea of changing your definition of equals and then examining the new shape, well, that's how you construct a torus mathematically. You take the plane and impose a new definition of equals, and suddenly you have a torus. And you impose your definition of equals. Your new definition of equals is saying you characterize your definition of equals by specifying the group of transformations that keeps you within an equivalence class, and that's called quotienting. And here's a sort of very basic visual example of it, and we will get into the details when we read Artin. Okay. How long has the video been going? I might not actually read Artin. 31 minutes. Let's at least look at Artin. Which one is the journaling program? Okay, let me go over here. Let's at least look at Artin. Okay, we're going to 1 or 2. We've already read through chapter 1. Oh my god. Can't believe I read all of that. Okay. Laws of composition, and let's just look at, kind of see the way he's framing it and maybe compare it a little bit to the way I was framing it. Alright, some quote in a fake language that nobody speaks. Laws of composition, Bourbaki, he glows in the dark hard. It was actually a conspiracy by the CIA. It was a bunch of different mathematicians who all conspired together and pretended to be one guy named Nicholas Bourbaki, and they also pretended to be French. Anyway, I think Artin's father was part of the Bourbaki group. I'm not 100% sure, though. Emil Artin is a towering figure of 20th century mathematics. Or maybe the century before that, I'm not sure. Emil Artin's a big deal. Michael Artin is also a big deal, but Emil Artin is a bigger deal. Michael Artin they're both big deals. Law of composition on a set S is any rule for combining pairs to get another element. Right, so this is what I said. He's starting with what the CIA wants you to, the way the CIA wants you to think about groups is not as things that symmetrize something else, but as a group that you think about on its own. Okay. Law of composition on a set S is any rule for combining pairs AB of elements of S to get another element, say P of S. Some models for this concept are addition and multiplication of CIA real numbers. Matrix multiplication on the set of n by n matrices, sets are another CIA psyop, is another example. Formally, a law of composition is a function of two variables, or a map, S times S to S. So that's what I was saying before. Here, S times S denotes as always the product set, whose elements are pairs AB of elements of S. The element obtained by applying the law to a pair AB is usually written as a notation resembling one used for multiplication or addition. Or whatever, a choice being made for the particular law in question, right? The element P may be called the product or the sum, depending on the notation or context. Right, we'll use product notation AB most of the time. Anything done with product notation can be written with another notation such as addition and will continue to be valid. The rewriting is just a change of notation. It is important to note right away that AB stands for a certain element of S, namely for the element obtained by multiplying the given law to elements denoted by A and B. Thus, if the law is matrix multiplication and if A is 1302 and B is 1201, so that then AB denotes 7 3, 4, 2. Okay, I'm not going to check that, but sure. That looks plausible. Once the product AB has been evaluated, the elements A and B cannot be recovered from it. Right. Well, if you know B, then you can recover A, assuming that B is invertible, and that matrix is definitely invertible. So, with multiplicative notation, a law of composition is associative if the rule ABC is equal to ABC. That's what I was saying before about how the CIA puts this other rule on it because you start thinking about the group on its own terms, rather than thinking of the group structure as sort of this weird aberration that shows up when you start considering symmetries. You rather consider the group structure to be fundamental, and the fact that it symmetrizes things as kind of an afterthought. In fact, he's not even going to talk about symmetries, I think, until chapter 6. Anyway, this section is only 3 pages, so I think I'll read it. Multiply the result. So, right, this is the associative law. So A times B times C is equal to A times B times C. It has to be associative. Yeah, we know what this means. Law of composition is commutative. Yeah, matrix multiplication is associative, but not commutative. That's important. It is customary. This is a custom to reserve additive notation for commutative laws, such that A plus B is equal to B times A, B plus A for, I don't know what I just said, A plus B is equal to B plus A for all A and B. Multiplicative notation carries no implication either way. I better be recording with the right microphone. I am. Carries no implication either way concerning commutativity. The associative law is more fundamental than the commutative law. Right, so the commutative law is not part of the definition of a group. I just want to make that clear. It's a subclass of groups called abelian groups, or commutative groups, but mathematicians like naming things after people, so abelian groups. Sorry if you can't read that notation. Abelian groups is equal to commutative. Okay, the angle of this pencil cursor is messing with my head, but I will deal with it. Because the angle at which that pencil cursor does not match the angle at which I hold the pencil, and it's anyway, it doesn't matter. Multiplicative notation carries no implication either way concerning commutativity. Done. The associative law is more fundamental, and one reason for that is that composition of functions is associative. So let T be a set and let G and F be maps or functions from T to T. Let Goff denote the composed map, T map, fuck this arrow shit, this curvy arrow shit. The customary notation is that, but anyway, that's what I was using before, is T backslash lead, this, so the reason I know I'm right is because his is backslash leads to, and mine is backslash maps to. And so obviously you should use backslash maps to rather than backslash leads to, but CIA's glowy's gonna glowy. Anyway, G, F, okay, right. This is a law of composition on the set of maps T to T. This law is associative, right. Right, exactly. Both of the composed maps send an element T to H of G of F of T. When T contains two elements, say T equals AB, there are 4 maps. The identity map, there are 4 possible maps on a set of 2 elements. Okay. So the identity map, a transposition, the constant function on A and the constant function on B. Okay, that makes sense. The law of compositions of maps can be expressed in a multiplication table. Right. I'm not going to check that multiplication table. F to G of, okay. That looks plausible. Okay. Thus, T of alpha is equal to beta, so that makes sense. You do the constant map to alpha, map everything to alpha, and then transpose, that'll map everything to beta. And alpha of transpose, so you transpose everything and then go to alpha. Okay, so composition of functions is not a commutative law. That's his point. Going back to how much longer do we have? Okay, only a little bit. Going back to a general law of composition. Suppose we want to define the product of a string of n elements of a set. There are various ways to do this using the given law, which tells us how to multiply two elements. For instance, we could first use the law to find the product A1, A2, then multiply. Okay. If you're associative, it doesn't matter. Right. Okay. Let an associative law of composition be given on a set S. There is a unique way to define for every integer n a product of n elements, denoted temporarily by brackets A1 to AN with the following properties. The product of one element is the element itself. I'm looking at number 3, and I need to start putting my face in the videos, because I think my facial expressions would be very funny. Like, when I see something like the third one, I'm like, what the fuck is that? Okay, some monkey notation. Anyway, A1, A2 of two elements is given by the law of composition, okay? He's saying that you can, if you're associative, then it doesn't matter how you group the parentheses, then, so you can just sort of talk about the whole word all at once. Okay, and he's proving this using induction. Do I really need to go through this proof? It's okay, I get it. I'm just skimming the proof. Yeah, I mean, okay, that's interesting. Induction is the mathematical word for recursion, so they mean the same thing. An identity, right, that's what I just talked about. An identity for a law of composition is an element E of S such that EA is equal to A and A is equal to A for all A and S. There can be at most one identity if E and E prime are two such elements. Then since E is an identity, E prime is equal to E prime. Okay, right. So there can be at most one identity because you can prove that composing the, here, I'm going to zoom in because this is god damn it. I'm going to zoom in because this is important. There can be most here, I'm going to put a nice star next to this. This is important. There can be at most one identity, for if E and E prime are two such elements, then since E is an identity, E prime is equal to E prime, and since E prime is an identity, E is equal to E prime, right? Thus they're equal. Yeah, matrix multiplication has an identity. For n by n matrices, it's the identity matrix. For the set of maps, it's the identity map, right? The identity element will often be denoted by 1 if the law of composition is written multiplicatively, and by 0 if the law is written additively. These elements do not need to be related to the one. Oh, right, this is wonderful notation, is overloading 1 and 0. It's common in math, but you just deal with it. So I gotta zoom out because I can't read it when it's this zoomed in. I can't, my eyes can't scan that distance. The identity element will often be denoted 1 if the law of composition is multiplicatively, and by 0 if the law is written additively. These elements do not need to be related to the numbers 1 and 0, but they share the property of being identity elements. So sometimes the identity is 1 and sometimes it's 0. That's the lesson here. So sometimes 1 is equal to 0 depending on your notation. Suppose that a law of composition on a set S, written multiplicatively, is associative and has an identity 1. An element A of S is invertible, right? So he's just sort of walking through, I think, he's walking through what each of those terms mean in precisely as much as he can. These properties are really important. It's worth... Okay. And then he says a group is a set G together. G would be the group of symmetries. So again, you're thinking about what is the structure of the symmetries, and then what you'll notice is that the same symmetry structure might symmetrize a bunch of different objects, which is interesting. And they might come up in totally different areas of math. One might come up in physics, and another one might come up in, you're studying some crystal or something like that. This group theory stuff is really, really important. So anyway, let's just read. Yeah, so the inverse is usually a to the minus 1, but sometimes it's minus a. We list without proof some elementary properties of inverses. All but the last have already been discussed for matrices. See exercise 1.3. Go look in your own books for exercise 1.3. There's a link to buy the book in the description. Go buy the book. There's an element A that has both a left inverse and a right inverse. Then L is equal to R, A is invertible, R is its inverse. Right. So yeah, so the way you prove that the inverses are unique, how do you do that? I think you say L. Oops, I should switch to a color you can actually read. Okay. First of all, these properties are important, so I'm putting a star next to them. Anyway, so what you do, I think, is you consider LAR, and this is going to be, because A times R is the identity, this is just going to be L, and then, but LA, because they're associative, you can also group it like this. Well, this is LA is equal to the identity because it's an inverse. This is equal to R, so therefore L is equal to R. That's how you prove that. Okay. If A is invertible, its inverse is unique. I don't know what that means. I think that's... There's only one... Oh, you can't have two different... Right, so if you have A times R and A times rho is equal to the identity, and A times rho is equal to the identity, then I think you can just do the same trick as above. So yeah, so invertible by definition means that the inverse is both left and right. So yeah, you can just do the same trick. You consider RA rho and just do the same trick as before, and you would get that this is invertible. Inverses multiply in the opposite order. So if A and B are invertible, so is the product AB, and AB inverse is equal to B inverse A inverse. Okay? An element A may have a left inverse or a right inverse, though it is not invertible. I talked about this, can't remember which video. I did a video very recent, it might have been the last one in the Abstract Algebra series, where I talked about how you tell if a function is invertible. I can't remember which video it was. What was I going to say? But I think it was Abstract Algebra 19 or 20. I remember clipping it up. Anyway, I'll try to remember to link that. But I talked about how you can have one type of inverse but not the other type in that video. So go. I'll try to remember to link that. Power notation may be used for an associative law. Right. So A inverse, right, okay. A to the 0 is equal to 1. Usual rules for multiplication of powers hold. Right. When additive notation is used for the law of composition. So these N and S and whatnot all have to be integers. When additive notation is used for the law of composition, the power notation is replaced by the multiplicative notation. Oh, this is wonderful, because now this n is not an integer and or n is an integer and a might not be an integer. So that's how you get wonderful things like, oh, and this is a completely different notation than the 12z notation that we saw before. Completely different note. It's just, mathematicians love overloading notation. I have said that mathematical notation is like C++ minus the constraint it has to compile. Well, you know, fraction notation is not advisable and right unless the law of composition is commutative, because it isn't clear from the notation whether the fraction stands for BA inverse or for A inverse B, and these two elements may be different. And notice that the quotient group notation uses the fraction notation. And so, is there such a thing as an inverse group? I'm not sure. I don't know what that would even mean. Okay, so this is what I said above. An abelian group is a group whose law of composition is associative group. So this is what we just saw. Anyway, and so next video will be 2.2 on groups and subgroups, I guess. Yeah, so here he's getting into the very basics of group theory. Then the subgroups of the additive groups of integers, showing that it's nz, which I told you before but didn't prove. He proves it. This is the Euclidean algorithm, I think. Cyclic groups. Yeah, you know what? This doesn't matter because we're going to read it in the next video. Alright, see you in the next video. Thank you for watching if you watched all the way to the end. How long are we? 52 minutes, not bad. Alright, thank you. Bye.